Okay, we had the question of collisions. Class wanted to go over collisions today. Had a very short class. Snow schedule shortened it and nobody showed up till about 15 minutes before the end of the time, but we're gonna extend it a little bit with some videos. Okay, anyhow, we did this much in class. Want to look at collisions in 2 dimensions. So the basic thing that happens in a collision of 2 objects in an isolated system is that they have equal and opposite changes in momentum because they exert equal and opposite forces on each other. And that comes about simply because you have equal and opposite forces for equal times. You have equal and opposite changes in momentum. That extends for object in 2 dimensions. While momentum is a vector quantity, it has 2 components. That means the change in the x component has to be equal of one object, has to be equal and opposite to the change in the x component of the other. And the same for the y components. So you can break the collision into 2 independent collisions. Okay, you can treat it as just a collision of the x components of the momentum, a collision involving the y components of the momentum. So we say that the collision, the force acts as 2 independent collisions, one in the x direction, one in the y direction. So you have momentum m1 v1x, where v1 is, okay, let's be careful. You got mass m1 at velocity v1, mass m2 at velocity v2. Okay, so v1 is v1x times I, if you wish, plus v1y times j. v2 would be v2x times I plus v2y times the j vector. And your momentum components in the x direction would be m1 v1x, m2 v2x. In the y direction, you have m1 u1x, m2 u2x, where u1 and u2 are the components of the after collision velocities. And then you have the same thing for the y components. You could just write the same thing, but you have y's written here. Okay? So just looking at the x, these are the 4 quantities that we have to deal with in the x direction. And then we can simply write out the impulse momentum theorem for the x component of the collision. Mass times change in velocity of the first object is equal and opposite to the mass of the second object times its change in velocity. Because that is the change in momentum, that is the change in momentum of the second object. So here we can say that the change in P1x is equal and opposite to the change in P2x. And P1 being the momentum of the first, P2 being the momentum of the second. Similarly, we can write the conservation momentum or the impulse momentum theorem for the y direction. And it looks just like this, except we're using y components. Okay, so for an example, let's say we have 10 kilograms at 8 meters per second at an angle of 53 degrees, and 6 kilograms at 12 meters per second at an angle of 323 degrees. Now this thing is moving faster than this, so this thing's moving along at 53 degrees, and this thing's moving along a little faster, 320 degrees, 323 degrees. They collide and they'll go off, something like this. Or maybe they collide and stick together and go off in one direction. In any case, give this information, gives us v1x, v1y, v2x, and v2y. v1x is being v1 times the cosine of 53 degrees, v1y being v1 magnitude of v1 times the sine of 53 degrees. We get these results in a very straightforward manner. And same thing for v2x and v2y. Okay, so we get these velocities, so now we can simply write down the equations that express the momentum change of each object if we have something to represent the final momentum. Okay? Well, the final velocity, again, this is an inelastic collision. The two things stick together, move off together. So in this case, using again u1x and u1y for the x and y components of the after collision velocities, u1x and u2x are the same. In other words, the after collision velocities of mass 1 is equal to the after collision velocity of mass 2. So we're just going to call that, in this case, ux. And same thing for y. u1y has to equal u2y, so we're just going to call it uy. Now we write down the expressions for the change in momentum for the first object and the change in momentum of the second object in the x direction. Okay, so 10 kilogram mass goes from velocity 6.4 meters per second to ux. There's our 6.4 meters per second. Second object goes from 9.6 meters per second to ux. Okay, that's the x velocity. So we have these relationships. Again, then 10 kilograms times the change in velocity of the first object is equal and opposite to 6 kilograms times its change in velocity of the second object. Mass of the second times change in velocity of the second. We write the same equations for the y quantities. We just read off the initial y velocity of the first object and of the second object. And we write down the equation. Hopefully we don't write it down without thinking about what it means, because otherwise we're not reinforcing it. We're going to forget it very soon. And then we just solve for ux and uy. And it's very easy because you have two equations and only one variable in each. Okay, so you have ux and uy. And then, of course, having found ux and uy, we can find the magnitude of u and its angle using the arctangent. Okay. Now, if the collision's elastic, and it's the same two objects, it's a little more complicated because here we have the simplifying condition that the after collision velocity of the first object is equal to the after collision velocity of the second. So we didn't have to distinguish between u1x and u2x or u1y and u2y. We could just call both of these ux, call both of these uy. So for each direction, we just got a single equation. Now we've looked at elastic collisions, so you know that we're going to get two equations, one indicating, or one being equivalent but much simpler than, equivalent to but much simpler than the condition that kinetic energy is conserved. That condition can be reduced to the condition that the relative velocities reverse on an elastic collision. So if the collision's elastic, the thing that we know is that v2x minus v1x, which is the relative velocity of the second object, the velocity of the second object relative to the first. Okay, so from the perspective of the first object, the second object appears to have velocity v2x minus v1x in its frame of reference. Okay? And here you have the same thing for the after collision velocities. And it's written down in the same order, but then reversed. Okay, so that the relative velocity here, the velocity v1 sees from its perspective before collision, well, after collision, it sees exactly the same speed but going in the opposite direction, so just a rebound at the same speed as viewed from object u1. Okay, and then the same thing for y. The condition for an elastic collision, the condition for conservation of kinetic energy. So we can easily then write down equations for the x motion. For the x component of before and after velocities. This equation is just like this equation, except of course, again, we have to distinguish u1x from u2x in this case. Well, having done that, we've got two variables here, which is why we need this condition, okay? And this condition, using the v2x and the v1x from before, because we're considering the same two objects, okay? Colliding inelastically, then colliding elastically. So using these two x velocities, we get the relative velocity before collision in the x direction, the relative x velocity before collision. And it's equal to the negative of the relative x velocity after collision. Now, mathematically, it's very simple. Now, this gives us two equations in the two unknowns, u1x and u2x. So we can easily solve. I would start by solving this equation for u1x in terms of u2x, or u2x in terms of u1x. If I solve for u1x, then I plug that in for u1x, and I'm going to have an expression in terms of u2x, and that's the only variable I've got in the equation, so I can easily solve it. Okay, and then we do the same for the y. Then we have the after collision velocities, and then of course u is going to have the magnitude and so forth, and angle that we figure out from the components. Okay, now next we want to take a look at a more complex, mathematically complex situation that if you look forward you can see we're going to end up with 4 equations and 4 unknowns. It's where we're given the magnitudes and directions of velocities of we're given the magnitude and direction of the before and after velocities of object 1 and the mass. So 6 kilogram mass has this velocity before and this velocity after. So we can easily find its change in momentum. Second object, however, we're only given its speed. We're not given the angle. So we're going to have to figure out the components of these velocities and the angles at which these velocities are applied. Okay, so we do that. There it is. In the next video, you can see how that works out.